In this video, I'll talk about energy stored in a capacitor. The energy stored in a capacitor is denoted by U. Sometimes we also denote it by E. But here, if I use E, then it will be more confusing because E is also used for the electric field. So instead of using E, we're just using the U as an energy stored. The energy stored is given by half CV square. As we know that Q is equals to CV, we can also express the energy stored in terms of Q, C and QV. You can use any relation here. So most of the time we'll be using Q equals to half CV square, and that keep in mind Q is equal to CV. If charge and the capacitance is given, then you use this formula. If the charge and the potential difference is given, then you're going to use this formula. If the capacitance and the voltage is given, or the applied potential is given, then you're going to use this formula to calculate the energy stored. The unit of energy stored is joule. Now I will talk about the energy density of a parallel plate capacitor. So in order to compare the effectiveness of energy stored in a capacitor, we compare it by calculating the energy density. Here I think I made one mistake here. This has to be energy density, not the energy stored. This is the energy density. Okay, so if we need to compare one capacitor to another capacitor, a bigger capacitor might store more energy and a smaller capacitor might store less energy. But how do you compare? In order to compare, we calculate the energy density. The energy density gives you how much energy it can store within a unit volume, or the energy per unit volume is called the energy density. Okay, so now let's say we have a parallel plate capacitor here, and we are interested in calculating how much is the energy stored. So the energy is the formula for energy density is energy per unit volume, and we already have calculated or written down the relation of energy stored, which is half CV square. So this is the energy, and the volume means this is the capacitor. This is the one plate, this is the second plate, and the volume is this volume. The volume between the two plates is the volume of a parallel plate capacitor. How do you calculate this volume here? We already know the cross-sectional area is A, and we know the distance is D. So this cross-sectional area times the distance, or the gap between the plate, gives you the volume, this volume here. Okay. So now we also know that for a parallel plate capacitor, the capacitance is given by epsilon naught A divided by D. Okay, so here I'm simply plugging all the formula. This is the formula for the capacitance, and the electric field value is the change in potential divided by the distance. So the V is equal to E times D. And here I'm just plugging out the value of V, which is E times D. And as it is square, I'm putting the square here. And the volume again is the area times the distance. That's what is here. Now the D square cancels out, D and D. This area and area cancels out. So what we left is half epsilon naught E square. What you can see here, the energy density depends entirely upon the electric field values and the medium. Here this is for the air medium. Now this is the epsilon naught is the permittivity for the free space. But now what happens if we fill this medium or the gap in between with some other material like paper, water, Teflon, some oxide? If this medium is filled, if the gap between the plate is filled with some medium, then we can write down the energy density as this formula here. Here I am adding one more term here, introducing one more term, which is the kappa. This kappa is called the permittivity, relative permittivity, or the dielectric constant. And this is a constant for the medium. For example, for water it is 80. So that means if we compare the energy density of the parallel plate for air and for a medium filled with water, then for the water the energy density will be 80 times greater than filled with the air, because the energy density, because the relative permittivity or the dielectric constant of the water is 80. So this kappa is 80 for water, which means the energy density will be more if it is filled with some other medium. Almost all capacitor are filled with some sort of the material or some sort of the dielectric material. Okay, so this kappa is the relative permittivity, and epsilon naught is the permittivity of free space, E is the electric field, and the unit of energy density is joule per unit per cubic meter. Okay, and this is a scalar quantity. So now again, if you have any questions with the energy stored in a capacitor or the energy density, write down your comments and do not forget to subscribe the channel. Thank you so much.